now the session becomes really interdisciplinary. I think I'm the only one which will make some comments on nuclear physics. I'll talk about quartet condensation in the context of nuclear physics, but presentation will be quite general. Actually, I should thank the organizers for inviting me. It's an interdisciplinary workshop which I appreciate very much and enjoy very much. So actually, here are my collaborators. You see there's a bunch of Japanese fellows which are essentially involved in the nuclear part, but maybe 15 years back with Gerd Röpke and Philippe Lauzière in Grenoble, who was also very interested in quartet condensation. We wrote actually 1 or 2 papers together about quartet condensation in infinite nuclear matter. I think I should have put Philippe Lauzière here on the list of authors, but I guess this is the only paper which Philippe Lauzière has in the nuclear physics journal. So, okay, let's go on. A little bit of the contents. General aspects of clustering or nuclear clustering, quartets and their condensation in infinite matter. Talk about critical temperature, quartet versus pairs. We'll see that quartets are quite different from pairs in some respects. Quartet order parameter equation and solution, and then I talk more about a rather interesting story about finite nuclear and nuclear systems. And you will see there are some interesting aspects to this. So, quartet, yes, quartet. In nuclear physics, we have, of course, also superfluidity. Gordon has mentioned this superfluid moment of inertia in nuclear physics. We have in nuclear physics one bound state of a dimer, which is a deuteron. On nuclear scales, it's very lightly bound, only 1 MeV. Fermi energy is something like 40 MeV. But the quartet, this is the alpha particle, which consists of 4 different fermions. And I stress here the aspect of 4 different fermions. Protons spin up, spin down, neutrons spin up, spin down. We have isospin in nuclear physics. This has already a tremendous increase of binding energy. Why? Because in a quartet, if you have about equal attraction here in all bonds, you of course have your 6 bonds with respect to 1 bond on one hand. On the other hand, the alpha particle is sort of the lightest doubly magic nucleus, where you have the lowest, in a mean field picture, the lowest level, which is the 0s level, completely filled. And this in nuclear physics, as in atomic physics, gives you always extra binding. So you have protons spin up, spin down, and neutrons spin up, spin down. And of course you have no bound for neutron state, because a neutron, you would be forced to put the 2 extra neutrons, the 3rd and the 4th neutron, in the p shell, which is energetically very penalizing. So this gives you, the alpha particle has a binding energy per particle which is 7 times more than for the deuteron, and is almost as strongly bound as the strongest bound nucleus, which is the iron. IR56, which is more maybe 8 MeV binding energy. So, and also there's one aspect which is very important, that the first excited state of the alpha particle is about 20 MeV, which is by factors higher than any other first excited state of any other nucleus. So it's really a boson which is very stiff and almost ideal boson in many respects. But nevertheless, we have to consider that these are 4 fermion states. And other quartet states in physics are not so numerous. But here we talked a lot of in the morning session about excitons. But I know in some systems there are also biexcitons, and nobody mentioned that, at least I couldn't hear anything about there's an old question in condensed matter physics. Do excitons condense as singles, or do biexcitons condensate, or what is the relation between both? So this is one aspect which is maybe important in this context of quartet condensation. Biexciton is of course also quartet. There are other things which may become important. Yesterday we heard cold atoms eventually by Tempere, who made the hypothesis that one may trap 4 different species, maybe potassium up down and rubidium up down. So it's not done yet, but maybe in the future there will be such possibilities that one traps 4 different fermions. Actually, there is already theoretical studies by a French guy who is and collaborators, Philippe Le Cheminot, who has made a DRMG calculation in 1 dimension with quartet possibility of quartets. They also have 4 fermion possibilities. They consider spin 3/2, which gives you the projection of the 4 different fermions. And actually, they were inspired by our works where they saw that, and we discussed that this quartet condensation can only happen at very low density. And this will be one of the important aspects of this. Now, we have, of course, as I said, also ordinary pairing. Deuteron is a bound state, so we can consider eventually the transition from BCS or from, does this work or something? I think this, yeah, I don't. Imagine a gas of very dilute deuteron, then you have certainly Bose-Einstein condensation of the deuterons because Pauli principles of acting between. But when you squeeze it, you get to the BCS crossover, and in this community, I don't have to tell that what happens. Still, you have superfluidity here, in spite of the fact that the Cooper pairs are extremely strongly intermingled. So this is the case of standard pairing, and we have standard pairing, of course, between proton and neutrons, and neutron and proton also have condensation. But what happens to the quartets? Something interesting happens there. Namely, you have, of course, for the quartets, the back phase. If you have alpha particles or any other quartets which are far apart, they Bose-condense. But this is one of the main messages I want to convey to you in this talk, that there is nothing like a BCS phase for quartets. Quartets don't have the possibility to develop a long coherence length, and that alpha particles get big sizes and intermingle with the. So this I want to explain to you where this comes from. So critical temperature for alpha particle condensation in symmetric and asymmetric nuclear matter. What is symmetric nuclear matter? Even number of protons and neutrons, so isospin 0. And asymmetric nuclear matter, like in neutron stars or something, where you have much more neutrons than protons. So these are relevant publications here, and we had also a Japanese postdoc. So how do you calculate critical temperature for quartet condensation? Well, you know how you calculate critical temperature for pair condensation. It's the Soulis criterion. You have to have in medium two-body. In medium, you have to solve an in medium two-body scattering equation, and if the eigenvalue hits 2 times the chemical potential as a function of the temperature, then you have the criterion. Here is a 4-body in medium equation, where it's essentially the same. Of course, you have much more terms here. You have 6 exchange terms. You have the 2-body interaction. You have the Fermi-Dirac Pauli blocking coefficients. These are the same as in the Soulis criterion. Of course, you have the 4 kinetic energies, and you have, if the eigenvalue hits 4 times the chemical potential for a definite temperature which enters here in the Fermi-Dirac functions, then you have the criterion for onset of quartet condensation. So it's exactly the same, only 2 times more particles. Well, you can imagine that it's extremely difficult to solve the 4-body equation with a nuclear interaction. It's already difficult to solve this equation with Fadeev-Jakubowski formalism and so on in free space for a single alpha particle. But now we have here in addition this very non-local Pauli blocking factor, so this makes things even more complicated. Fortunately, in the nuclear community, we have Rimas Lazauskas, who is an expert in solving 4-body and 3-body equations, and he could solve these equations fully with a relatively realistic nuclear interaction, and we could calculate here the critical temperature from solving this equation. Of course, in general, some approximations are demanded because these are extremely complicated calculations. We came up with a very efficient approximation to this condensate wave function. I don't have the time here to explain what type of approximation it is, but it worked extremely well, this approximation, and made the calculation extremely faster. So this is the critical temperature for alpha particle condensation. Here's the alpha particle condensation, here's the deuteron condensation. So the alpha particle as a function of chemical potential, of course, starts out here at the energy per particle, which is -7 MeV. And then immediately, if the density goes up here, here's the corresponding plot as a function of the density, critical temperature shoots up and comes here to a maximum, which is about 8 MeV, which is at these densities similar order as the Fermi energy. The crosses are the exact solution of this 4-body equation with relatively realistic nuclear interaction. The full line is the approximation which I was mentioning, which I don't have the time to discuss here. So alpha particles start at -7 MeV to condensate. Deuterons start at half of the binding energy, which is -1.1 MeV. And then comes this surprising phenomenon that for alpha particles at some value of the chemical potential which is close to 0, 0 means Fermi energy, the alpha particle condensation breaks relatively suddenly down, and deuteron condensation goes on. And this is the phenomenon I was mentioning in the beginning, that alpha particle only have a back condensate phase, and not for higher densities. If the density comes such that the alpha particle starts to appreciably overlap and become into another way, the quartet condensation in general breaks down. And this has a very general reason for that. Here is the same plot as a function of density. So this quartet condensation here breaks down at very low density. Nuclei have a so-called saturation density. Let's call it rho 0. And this breakdown here is at very low density already, namely at rho 0, a fifth of rho 0 of nuclear saturation density. Here are some wave functions which start to oscillate. I don't have time, as in the BCS case. If you go to higher densities, they develop something here. So I don't have the time.
What is rho 0?
Pardon me?
What is rho 0 for people who don't know? That's the
You want to have the number?
No, what do you mean by
Rho 0, I mean, nuclei have a saturation density. This is the surface, and this rho over R as a finite nucleus, and this value here is called the rho 0 density. This is the density of
The balance between cool and
This is the balance because it's short-range interaction. So as a function of particle number, you don't gain energy anymore, contrary to the Coulomb interaction. Okay, next slide. So we also calculated this as a function of asymmetry. Asymmetry nuclear matter, which means more neutrons than protons. So this is important for, say, compact stars, collapsing stars, and neutron stars, where you have very little protons with respect to neutrons, depending where you are in a neutron star. And of course, as for polarized Fermi systems, since we are proton-neutron, if it's not symmetric, if there are more neutrons than protons, this hinders deuterons superfluidity, but also alpha particles superfluidity. But since the alpha particle is much more stable and much more bound than the deuterons, in the asymmetric case, if you go up with the density or with the chemical potential, finally the alpha particles win over here over the deuterons, whereas at symmetric case the deuterons win here over the quartic condensation. So the less bound deuteron, much less bound deuteron, as a function of asymmetry, disappear much earlier than the alpha particles. Alpha particles stay on as rather large, asymmetric, like they are in neutron stars or so forth. So it's the same thing as a function of the density. So now let's come a little bit to the theory, how we treat then fully the condensed phase of alpha particles. Well, if you eliminate from the 2x2 BCS equations, you can introduce an effective mass operator in the ordinary pairing case, where you incoming fermion and with opposite momentum you pick up and you go into the condensate. So then the mass operator is a gap squared over E plus the single particle energies. And in principle, you have also some occupation factors here, but they add up to unity because F bar is 1 minus F, so you have a unity here. Whereas if you have a quartet, and this is now the crucial difference. If you have a quartet, you have an incoming fermion, and you have to pick up 3 fermions out of the Fermi seed to form a quartet condensed state. And then if you calculate this graph, you have here a quartet gap function with 4 indices instead of 1 here. Here's a diagonal. And 3 kinetic energies in the denominator. And what is most important is here that these occupation factors, which are F bars, which are essentially particle occupation factor product of 3 plus the whole occupation factors, does not sum up to unity. So they remain as the factors. And then let us calculate what is most important here, the level density of this 3-hole propagator here. And you will see that there is an essential difference between a 3-hole level density and the 1-hole level density. This is done here in this view graph. As long as you are, here's the 3-hole level density which enters into this gap equation. This is here the energy conserving delta function, but you have the prefactor with the phase space factors F bar plus F, which I just pointed out. This corresponds to this 3-hole propagator. As long as the chemical potential is negative, these at least at 0 temperature, these factors are just add up to 1, and you have here for negative chemical potential, you have the same feature as for pairing. There's no problem. But as soon as you come with the chemical potential to positive values, no binding anymore, this level density has, at the Fermi energy, goes to 0. So here we have different chemical potential, low density, and there's a higher density. And why does this go to zero? This comes simply from the fact that energy conservation and phase space cannot be fulfilled at the same time. And this is a very general feature which holds for all quartets, and you're very familiar with such things, namely any level density which consists of more more holes at zero temperature goes through zero at the Fermi level. You know, a very good example for this is the mean free path in a Fermi system. To calculate the mean free path in perturbation theory, you need the two particle, one hole level density, and this goes through zero, and then the mean free path is infinite also. And this is the case for all level density besides the single particle level density and the two particle level density if the pair is at rest. So the pairing is a very exceptional case where you can go on beyond 5 minutes. Okay, I should come to the nuclear case. Where you can go on beyond the Beck regime. So just mention this. In the single particle case, you have not this problem. So finite nuclei. There's a rather interesting story. I mean, the only nucleus which has an alpha particle structure in its ground state in quotation mark because it's even unstable, but it lives very long, is beryllium-8. So this is a ab initio calculation with green function Monte Carlo from the Los Alamos group, Viringa et al. In the intrinsic system, you see very well two alpha particles formed, and they have some overlap, but is relatively weak. One thing which has to remark immediately is that if the two alpha particles collapse as an ordinary nuclei, the density is much higher. The average density of the object is about 1/3 from ordinary density, like I pointed out here, the row 0. So this is a very low density object. Now the question is, what happens if you put here a third alpha particles? You could imagine cartoon-wise that this has such a shape, and the third alpha particle means carbon 12. You have 6 neutrons and 6 protons. But we know that the ground state of carbon 12 has not at all this shape. It collapses to a dense Fermi gas, which in first approximation can be described by a mean field approximation. Nuclear physics are used to mean field with effective functionals and so forth, like everywhere else. So it's not at all such type of thing. But the question is, maybe as an excited state, such an object exists, and actually it does exist. And there's a funny story about this. In 1952, astrophysicist Fred Hoyle postulated on anthropic grounds that in carbon 12 there should be a second, besides the ground state, which is a 0+ state, there should be a second excited state of 0+ at around 7.6 MeV. This state in 1952 was not known. So Hoyle said, because we are made essentially out of carbon, and since beryllium-8 is long-lived but unstable, nevertheless it decays in 10 to the minus 17 seconds. It's long time on nuclear scale, but it's very short on atomic scale. There must be a bridge where a triple alpha reaction, alpha plus alpha plus alpha, goes first to beryllium-8 and then fast with a third alpha particle into a carbon state. And he said this reaction must be accelerated, and only way to accelerate it that there must be a 0+ state at this around this energy, because it's easy to calculate where it should be. And he went to Fowler, I don't know, maybe some of you know this story, and asked him to search for such a state. And in a couple of months, Fowler and his crew has found this state. And a little bit sad story about this because Fowler afterwards got Nobel Prize, but Fred Hoyle was very angry because he didn't get it. But this is history, and so forth. So, but nevertheless, in nuclear physics, for many years and even decades, the structure of the state was very mysterious, and we then postulated that this state is actually extended density states, like the cartoon I was showing before, where 3 alpha particles are at a higher density and can be formed individually, like in the beryllium-8. And then, since these are bosons, they eventually can condensate. Condensation is, of course, a big word. I mean, we have also superfluid nuclei, in spite of the fact that we have only a couple of Cooper pairs in the nucleus, with respect to the ground state, which is just a Fermi-gas. So we made a calculation, which is with a condensate ansatz. Here you have 1 minute, okay. In analogy to the number conserving BCS state, like Leggett wrote it down, for example, antisymmetries product of Cooper pair wave function, we make an antisymmetrized product of quartet wave functions. And for the carbon 12, we have, of course, 3 quartet wave function. It's in principle a tremendous task to calculate this. But we made a very good variational ansatz. I have no time to go into it. And these are these things. So, without any adjustable parameter, we could fit all the properties of this so-called Hoyle state now. This state at 7.6 MeV in carbon is called the Hoyle state in nuclear physics. And for example, here is the inelastic form factor, the inelastic electron scattering from the ground state to the excited state, and we immediately got complete agreement with this experimental data, and we could reproduce all the properties of the Hoyle state. One last slide before I come to the, and then we looked at the occupation numbers. It was only occupation numbers. We have the single particle density matrix constructed as the center of mass of the alpha particles. We diagonalize them in the ground state and in the Hoyle state. And you see the ground state is completely 100% compatible with an ordinary mean field. I don't explain, but this is just 3 S, D, and G waves. But in the Hoyle state, we have 70% of a pure 3 boson state. I mean, the alpha particles overlap a little bit, and there's some scattering out of the condensate. But essentially, you see there's a factor of 10 difference between the next occupation numbers. So this is a clear criterion for that the alpha particles are more or less free, is all condensed in the 0S state of their own mean field. So I'm running out of time. So we calculated this Hoyle state as an alpha condensate, 70% in the 0S state in their own mean field. There's a second 2+ state now, which was discussed much in nuclear physics. We interpreted that we just lift one alpha particle out of the 0S state into the 0D state. And there's a third 0+ state, which we then think is in a higher nodal S state. So I've finished my just conclusions. So, treatment of quartet condensation, we treated a la Gorkov. Actually, I made a mistake here. It should be 4-body correlation functions, which of course are difficult. We calculated the critical temperature for alpha particle condensation nuclear matter. The most important point is that the alpha particle condensation only exists in the back limit. There's no BCS phase for quartet condensation or any higher clusters. The pairing is an absolute exceptional case. And theory predicts that the Hoyle state is 70% an alpha particle condensate. It is a precursor of alpha condensation in matter which eventually may exist in compact stars. We have more alpha particle states, oxygen 16, neon 20, which are multiples of alpha particles. So this is active research in nuclear physics. Thank you very much.
Thank you. Very nice. Questions?
So I guess I was not sure about, when you say something about projective mean field theory, what does that entail?
Well, then I have to explain to you what is the approximation we did. Well, we just said we know in nuclear physics that alpha particle can already treat it in mean field theory as long as you project to a good center of mass momentum. You take the spurious energy out of it. So we made an ansatz which is same wave function 4 times in momentum space, k1 and so forth up to k4 under the condition that total momentum k1 plus k2 plus k3 plus k4 is 0. And if you take this as variational ansatz, you get complete agreement with the full 4-body equation. So it's of course a tremendous simplification because then you have to only iterate one 0s wave function. So this makes the 4-body calculation extremely more simple. Of course, it's only valid if you have a really good, strongly bound quartet. Diexciton is very slightly bound, so it may not be valid for the exciton. I'm looking also for maybe metallic hydrogen, discussing with Igor. Maybe the H2 molecule is relatively strongly bound. Maybe one can incorporate such quartet theory also for metallic hydrogen.
So can you do biexcitons in bulk?
Well, more difficult because first of all this approximation doesn't work because biexciton is very slightly bound only. Second, long-range Coulomb makes solution of the 4-body equation even much more complicated.
It's a missing link in the search for excitonic superconductivity in Cooper's oxide.
Yeah. I mean, this is I think an open question whether the excitons condense as singles or as doubles, as molecules.
And another question.
Let me just say, supposed to in these bilayer systems, of course, there are repulsive interactions between the excitons.
Yeah.
No light.
Yeah. Sure. I mean, contrary to nuclear physics, in biexcitons, even in semiconductor, you always have a repulsion between the same species. Whereas here we have always attraction between all species. So this makes it
More complicated.
Oh, last question.
Very quick one. So if I look at the plot that you showed of the exciton, not exciton, the alpha particle and the deuteron condensation in the back element, they're not coexisting. They're just two separate calculations, right?
They're not contiguous. They're separate calculations.
Okay.
Actually, it's for us is an unknown question how the transition goes precisely. I mean, we made separate calculations, but to calculate the transition, it's also a rather difficult but interesting question.
Good. Let's thank Peter once again.